So, Feryal, tell me about how you got into your field. Give me a little bit of your history.
I think, interested in physics from
Mm-hmm.
an early age. I remember being in third or fourth grade and being really interested in like what are atoms made of, what makes up the universe.
Right.
So I continued on that path, and then eventually between my undergraduate degree and graduate school, I realized I want to treat the universe as a physics
Mm-hmm.
laboratory.
That's
And
interesting because a lot of people start getting scared of physics at about third or fourth grade. So, it,
no, I would literally tell everybody who would ask me, what are you
uh,
going to be? I would say an atomic physicist because that's what I knew at the
okay.
time. And then it became, well, particle physicist or astrophysicist. And then
Mm-hmm.
that just took me down the path of looking at the things in the universe that are really at the extremes of physics, like black holes and neutron stars and
Right.
early stars and things like that.
And of course, the neat thing about going in the astrophysics direction is you're still dealing with the fundamental nature of matter. So you're dealing with the inner universe as well as the outer universe.
Absolutely, yeah. So there is just more happening in the universe than we can reproduce on Earth.
Mm-hmm.
So you can still do the basic, like fundamental physics, but
Mm-hmm.
the types of phenomena that you're looking at are just so much more broad than what you do on lab,
Mm-hmm.
in a lab on Earth. So it's a nice intersection.
So maybe for people just unfamiliar with how we can even understand or know that we can understand compact stars and exotic states of matter out there in space with no, with indirect methods of sensing from
Yeah, we don't
astronomy.
travel there
Yeah,
for
so
sure.
how have we become confident that we can understand these things?
Yeah, so I call us cosmic detectives actually because we're not there to really see the crime scene. We don't have firsthand either while the things are happening, we don't get to observe it. We're more like passive scientists rather than setting up our own experiment. But we actually have great tools with which we can reconstruct what happened. So, for example, we can separate light into its components. And we can do that here. And when you look at a tube of hydrogen gas versus a tube of neon, you see different colors when you separate it into its components. So then you take starlight and you separate it into its components and you say, I know what's in there. It's hydrogen or helium or for some more evolved stars, like different types of elements. So everything that we can do in a controlled way on Earth and learn about matter, we can use it for example, what happens to matter around a black hole? Well, we still use the same diagnostic techniques, just like a detective would, and then we reconstruct what happened, why it happened that way, where did the energy come from, what are the elements there, and so on and so
Right.
forth.
And I think it's probably surprising to many people who are aware of compact stellar remnants that we've gone far beyond proving their existence to actually talking about their detailed properties.
That's right,
So,
yeah. So proving their existence comes in a couple of different ways. For example, for black holes, how do we know that black holes exist? One of the best ways to verify that the black holes exist, both small, what we call stellar mass black holes within our own galaxy, and huge ones, anywhere from million to billion times the mass of our sun, out in the center of our galaxy and other galaxies, is to look at stuff happening around them.
Right.
So the analogy would be, let's say you saw our solar system from a distance, but for whatever reason you couldn't see the sun. But you could see all the planets moving around it. Just by looking at the motions of the planets, Kepler taught us 300 years ago how we could infer what is at the center, how much mass it has, and what properties it should have.
Right.
So we do that with black holes. We don't see the black hole itself, but let's say we can look at stars moving around it, and we can really trace out their orbits in a very detailed way. Especially for the black hole at the center of our galaxy, there is now 20 years of data covering the nearest stars to the
Right.
black hole in exquisite detail. So you basically say, okay, I do the same Kepler problem. I look at how the stars are moving, and then I infer that there's a 4 million solar mass
Right.
object at the center that's causing these stars to move this way. Oh, why don't I see it? So, and how, what kind of a volume is it confined to? So you just do this reverse
And
problem.
I've heard some people even argue that the evidence for this galactic center black hole is the best evidence we have of any black hole, even better perhaps than the individual cases of stellar mass.
I would say so because we have so many different types of evidence for that particular black hole. For stellar mass black holes, we again look at what, we don't see the black hole itself, but we look at what the companion star is doing. So it's in a binary, there's another visible star orbiting it. So we trace out their orbits and infer what the how big the black hole is and what are its properties. But there's more ambiguity, I agree with you, in those cases than the black hole, which we call Sagittarius A star at the center of our galaxy.
Right.
We look at the motions of orbits, we look at the gas, what the gas around it is doing, because that's also swirling around.
Right.
We look at how variable it is. So from 1 minute to the next, how much does the flux in that gas change? So there are many different lines of evidence for the existence of a black hole there.
And how close do you have to be to a black hole or any compact object before the deviations from Newton's theory are clear enough that you're probing that regime?
You have to be fairly close. Well, so for the center of our galaxy, we can see the deviations in. We would be able to see the deviations from general relativity in the orbits of the stars
Right.
when they are a few thousand Schwarzschild radii
Right.
away. And the Schwarzschild radius is basically that point of no return for the black hole.
Right.
So that's what defines the border, if you will, between the signals that we can get and the signals that we can't get. So because it's a fairly big black hole, you can be relatively farther away and still expect to see some of the predictions of general relativity.
Right.
It's kind of like the Mars situation in our solar system. Newton's theory is not sufficient in explaining the motions of Mercury. I'm
Right.
sorry, I meant
Sure.
the closest planet. So when you look at the orbit of Mercury, you already know that Newton's gravity is not sufficient. So.
Right. Now, does nature know how to make black holes of any mass? I mean, what are the ranges that have been observed, and is it possible to have, what are the low and high limits?
That's a very good question. We actually don't know exactly the answer to that. It seems that there are certainly black holes made from normal stars that happen to be fairly massive, maybe 20, 30 times the mass of our sun. At the end of their lives, they enter this exciting phase of being a black hole. It also seems like 10 billion times the mass of our sun is a possibility. There are at least a couple of black holes in other galaxies where the mass seems to be fairly close to that.
Right.
I'm not sure about anything in between. What are the seeds, the beginnings of the black holes that end up at the centers of galaxies? That's an open question that we're
Right.
ferociously working on. Another puzzle is that when you look at the smaller guys, like in our own galaxy, now there are 22 confirmed black holes in our own galaxy. You expect the smallest mass that we measure there to be around 3 solar masses. Instead, it's at about 5 to 6 solar masses, that lower limit. So there seems to be a gap between their closest cousins, which are neutron stars, which still have a surface and extremely dense interiors, the densest form of matter, but then you push them over the edge and they should become 3 solar mass black holes. Why don't we see them? That's an open, puzzling question.
Yeah, very interesting. And since you've raised neutron stars, that's a specialty of yours. Let's talk about them for a while.
Sure.
I mean, for me, it's interesting that theory-led observation quite strongly there. I mean, for a couple of decades, right?
That's
the theory
right,
was
yeah.
out there saying these things should exist, and then we didn't find them. So talk a little bit about that history or how that came about.
Sure. So it's true that the theoretical considerations first suggested there should be stars out there that are the burnt out remnant cores of normal stars that can't support themselves like normal stars do against the gravitational inward pull. So they should go into a form of matter where protons and electrons combine to make mostly neutron matter, and that's why we call them neutron stars. But this was several decades before we saw any observational evidence that they existed. So with this kind of theory in mind,
I should turn that off.
the first observational evidence for their existence came from what are called radio pulsars. So neutron stars that have a big magnetic field and they're spinning around their axis. So when you spin a magnet, you make you release a lot of energy, and in this particular case, this energy was released being as radio waves, radio pulses actually. So every time the star rotated in our line of sight, we would see this big radio pulse coming from them. Initially, it was unclear what these were. I mean, there were even scenarios that these were little green men at extrasolar civilization.
Right, because the pulses were as good as the atomic clocks of the
They
time.
are, because you pack so much mass into a very little volume. Think of how beautiful a spinning ice skater looks, and so take that and of course make it so much more compact and spin it around the star's axis. So the pulses become extremely regular. So the initial thought was maybe this is some kind of a signal from an alien civilization, but quickly that turned out not to be.
Yeah, I heard that Jocelyn Bell used to joke about LGM 1, 2, 3 on the pulsars.
Where LGM is little green men.
Yeah.
Yes, exactly.
Now, in terms of the theory, the prediction wasn't made of pulsars themselves. So
No, that's true.
So someone had to connect the dots.
Yes, and the dots were connected fairly quickly. So again, the things that we suspected these stars would have would be quite a bit of mass, so at least maybe yeah, I can start over so you can edit it. Yeah. So the things that we know from theory would be that they would have quite a bit of mass, at least as much as our sun, but probably more, and that they would be packed in a very, very small space, so about 10 miles across, 10, maybe 15 miles across, like the entire diameter, and that they could spin, but how they would actually emit light in a way that we could see was not worked out because they were so hypothetical.
Right.
So once the radio pulsars were discovered, then there was more detailed research into, these should possess magnetic fields just like stars do, and if you spin a magnetic field fast, then it could have the energy generation that could explain these radio pulses. However, I should say that even though at the radio pulsar phase of what we knew, it was clear that they were neutron stars. I think the more exciting development was when we started seeing them in the X-rays. And the reason for that is X-rays are more energetic and they probe phenomena that are even closer to the neutron star surface. So you're not looking just at the big magnetic field surrounding the neutron star, but you're getting close to the high temperature and density and gravitational field that is associated with the surface of the neutron star. And that emission comes out in the X-rays. So when we started being able to detect neutron stars, either because they had a companion or their surface was glowing because they were young or they were accreting matter, they were getting matter from a companion star, then I think the potential of neutron stars as a physics tool became
Right.
even more fascinating.
And is it? I don't know the statistics, but presumably there are the things we can observe, either pulsars with radio or the X-ray observation. That's a subset of a large population of neutron stars, many of which are undetectable.
That's right.
And what do we even know? What can we put a number on in the Milky Way? How many neutron stars there are roughly?
It's hard to say because we don't exactly know how much of the, for example, radio pulsar population we're missing. It seems like we're missing a lot because we don't cross the beams, or they're too far away, or they're just too old. So they just ran out of that energy that they can extract from their spin. So they're no longer producing detectable radio pulses. It's a gray area exactly when that stops happening. We don't know.
Right.
So it's hard to put a number, but it's a large number. So I would say that a fraction of a billion is a reasonable
So the
estimate.
pulsar catalogs are thousands, I guess. So we're
They're
only
thousands.
really looking at a small tip of the iceberg of this.
Absolutely tip of the iceberg. And this is despite the powerful new telescopes, both in radio telescopes that do large surveys now at different frequencies, and their sensitivity is so much better than what we had. And in other wavelengths, like I said, in gamma rays, for example, the Fermi telescope enabled detection of new radio pulsars that are so energetic that they actually not pulse only in the radio, but up to gamma rays, which is the highest energy photons that we
Right.
detect. Despite that, I think the catalog is now nearing 3,000.
Okay. So look, paint me a picture, because it's an extraordinary state of matter. I mean, there's something the mass of a sun that's the size of a city that's spinning dozens, maybe hundreds of times a second in some cases. But
Yeah.
what's the state of matter, and why is it so interesting to study?
It's interesting because it really pushes our understanding of what happens to nuclei. So we have a theory that says nuclei are made up of quarks. So protons and neutrons are made up of up and down quarks in different combinations. And we never observe quarks on their own. They're always bound in these proton or neutron states and some other types of combinations that they can form. So the question is, when you start squeezing matter to such a high density that neutrons and protons physically start overlapping, do they still behave like these bound states of quarks, or do they start behaving more like free quarks?
I see. Okay.
And this is not a question that we have been able to answer from first principles at all.
And of course, if accelerators can't get you there, I mean, they give you they allow you to project that quarks exist and what their properties are, but you never can simulate this state of matter.
You can never simulate it for two reasons. One is in colliders, first of all, you don't get to the densities that we're talking about in the neutron star cores. And second, when you create those or similarly large densities, you also jack up their energy a lot, so they become hot and dense, whereas neutron star cores are cold and dense.
Okay.
So it's even a more different regime of matter than even if we could go up to a higher energy in the colliders, it's not necessarily going to tell us whether matter transitions into a whole new state in the cores of neutron stars. So it's very exciting from a particle physics, nuclear physics point of view, because we just want to know. I mean, one of the things that we can say is, well, if you squeeze grapes enough, eventually you get grape juice. But does it work that way when you're talking about nuclei? When we squeeze them together enough, do we really get quarks?
And these are still interesting questions, because a lot of people read that the Standard Model just got a bow tied around it with the Higgs and so on. It's not that we know so much about these subatomic physics that they're not interesting things we might observe, or phenomena that we haven't predicted.
Yeah, I think the Standard Model has been successful in a lot of explaining a lot of the phenomena that we see, but Standard Model doesn't really include what is called quantum chromodynamics, which is the description of the interactions of quarks. So we can infer, like you said, that quarks exist, and we know roughly the masses of some of the quarks, at least. The lighter quarks, we don't know as well. But from that to explaining actually how they interact and why on Earth would 2 or 3 quarks have to be bound together in any observable situation. I mean, what happens to a solitary quark that we just can't separate it and observe it? So we're far from answering. I mean, we have phenomenological models that tell us why that might happen, but we're far from direct proof of that.
Let's talk a little bit about the issue of magnetic fields, because they're phenomenal entrained magnetic fields in neutron stars, and that must lead to another set of phenomena that you can't observe anywhere else. So how does that go?
That's absolutely true. So the highest magnetic field that we create on Earth is in the Florida Magnet Lab, and it's a transient field. So we can create it and it stays on for a while and it dies off. So neutron stars can create magnetic fields that are about 1 billion times stronger.
Wow.
I mean, it's just mind-boggling how much energy there can be in their magnetic fields. So that has its own, like you said, fundamental physics questions. So, I mean, let's start with the simplest one. You take vacuum, right? You just, no particles even, and you put such a magnetic field on it. Now, vacuum is not completely empty. It has virtual particles that are continuously being created and destroyed. So, electron-positron pairs. Now, electrons and positrons have opposite charges. When you put such a huge magnetic field in vacuum, these virtual particles actually feel a different force on them because of this magnetic field.
Right.
So you make vacuum into a bit, I mean, I guess you could call it a crystal. We say it's birefringent, so it just separates light into its components, even though it's vacuum.
Right.
So then if you were passing light through this medium of just vacuum with a magnetic field on it, it would do funny things as if it's going through a crystal.
Wow.
So
it's a nice cultural aside that most people find a vacuum boring, but to a physicist it's very interesting.
Vacuum is interesting, yeah. In fact, the more complicated your problem, the more you want to study what vacuum does, or the more complicated your physical law. You first want to understand what the vacuum does before you understand what the particles do. But in this case, really, it's the virtual particles in the vacuum that start acting differently, and they start interacting differently with light that passes through it. So that's why we say it becomes a crystal.
Right.
So there is a class of neutron stars called magnetars. Well, as the name suggests, they are very strong magnetic fields. So we want to see this vacuum phenomenon happening around them when the magnetic fields get so large and there is some light that is emitted from the star. Initially, it is in the surrounding material of the star, but from that it travels into empty space, like basically vacuum between the star and us. So we want to see this transition of what happens in that.
So put a number for Guinness Book of Records purposes. What's the highest magnetic field roughly that's been seen in
10 to the
magnetar?
15 Gauss is what we.
And a refrigerator magnet is what, a few Gauss or something?
It's, I mean, Earth's magnetic field, I think, is. No, the sun's magnetic field is 50 Gauss.
Wow. Okay.
So.
And all of the things you've just said, of course, are equally or more true for the vicinity of black holes too, and I guess that's just a regime where we don't have a lot of observational ways to test the physics near the event horizon.
That is true. So what makes neutron stars interesting is the fact that they have a surface, and this magnetic field is anchored somewhere in the crust of the star, and so on. When you come to black holes, the surface is replaced by the event horizon, that point of basically no communication between the interior and an observer outside of it. But actually there are a couple of really interesting things happening right now that might shed more light, and no pun intended there, in what happens around the event horizon. The first thing is We is a large collaboration that involves MIT, University of Arizona, Hawaii, etc. Are building a telescope that will have the resolving power to look at the event horizon around of the black hole in the center of our galaxy.
Right.
Now, it's so far away, even though it's
27,000 light years.
27,000 light years. So even though we said it's 4 million times the mass of our sun, it's actually a tiny, tiny object in the sky. So the angular size that it spans is very, very small. So there is no way we can build one telescope that will have the resolving power to look at that. So instead what we do is connect a whole bunch of telescopes that look simultaneously at the galactic center and basically turn the entire Earth into a big dish. So you carefully place these telescopes so that one of them is in Hawaii, the other one is in Chile, the other one is in the South Pole, the other one is somewhere in Europe, the other one. So we just have this network of submillimeter telescopes that can take data simultaneously, and we can combine, because our clocks are so sensitive, we know exactly when the light arrived. So we can, after the fact, combine the signals from all of these telescopes. This is called the Very Large Baseline Array. But this particular experiment that we are running on the Very Large Baseline telescope is called the Event Horizon Telescope, for obvious reasons, because what we are really interested in is being able to resolve the event horizon of Sagittarius A star at the center of the galaxy. So
and just to jump to the general situation, I mean, the existence of black holes is beyond reasonable doubt demonstrated, but the existence and nature of an event horizon hasn't been tested, right? So this is
right.
in a new area of testing the theory.
Absolutely. So this is, we were talking about earlier, when can you expect to see deviations, for example, from Newton's gravity? Well, yes, I mean, even in the stellar orbits, if they're close enough, you can start detecting these tiny deviations. But now we're actually more ambitious. We're saying, well, can we detect deviations from Einstein's general relativity? Because if anything, you would see those deviations around the event horizon of a black hole. So I think our first goal would be to see the shadow that is associated, like this this blackness surrounded by brightness. That is what we call the shadow. That is the signature of an event horizon. So
now, what does that mean, given that the light is bending anyway? So you're seeing behind the object anyway. So in what way is it a shadow?
So the center still looks dark. So the way that light is bent, the brightest part of the gas is in a photon ring, and that has a particular size, and it's always circular. So that should stand out against the middle part, which is dark.
Oh, so this is a brilliant signature. I mean, you won't mistake it for anything else.
Absolutely. And if you do it at the right wavelength, you also don't care that there is more gas around it. You really can tune it so that all the photons that you're seeing are really from this innermost region closest to the event horizon. So there are, I mean, we can show pictures of this maybe that shows beautifully how the bright ring stands out against the darkness. So.
And what's the time scale for this project? It's so exciting.
It is so exciting, and it's going on now. So the first sets of data were taken just a couple of years ago between Hawaii, Arizona, and California. So there is more data being taken right now with these baselines, but the more exciting thing is going to be when we hook up ALMA to this network, and that is an investment. It has to have the right receivers, etc. So there is a lot of work in connecting ALMA to the rest of this network, and then the South Pole telescope, because again, the bigger your the bigger the separation between the telescopes, the
Right.
more of Earth's diameter you're using to resolve the galactic center.
Right.
So within a few years, I mean, it's not that far away. Within a few years, we want to take the first true picture of a black
Wow.
hole.
And that'll be front page New York Times for
I
sure.
hope so.
Yeah,
It's
yeah.
yes, it's something that we're very excited about.
Great.
So taking the picture is the first goal, and then looking to see if that image really matches Einstein's predictions, general relativity's predictions, is the second goal.
Which is, of course, testing general relativity, which has passed its test with flying colors, but in a new regime, right?
Completely new regime. So it could pass the test with flying colors in the solar system, but still behave completely differently
Right.
by the time you get near the event
Right.
horizon of a black hole. So
Okay.
that's,
Great.
yes.
Okay, I want to ask one more question about your field and your, to get a sense of how the research works. So you have as a theoretical astrophysicist, you're interested in accretion physics, and give a sense of how when you have a toolkit you can apply it, because we've been talking about vastly different scales and objects, and
Yeah.
how you've worked on reionization, early universe, recent universe, stars, some huge black holes in the center of our galaxy. Talk about the power of the toolkit, when you're talking about all these phenomena, and they share common features.
They share common features, indeed. So it connects back to maybe what we were saying earlier, that we expect physics to behave the same way in different settings as long as we understand what matter is doing. So we always have light interacting with matter, and that's, of course, what we ultimately observe. What comes to our telescopes, and we break it down into its components, its wavelengths, we look at how it varies over time, etc. So one of my specialties is looking at how light interacts with matter under different conditions. Sometimes when you put a magnetic field on it, sometimes when something is exploding, sometimes when the first stars are forming and all the gas around them is neutral. So when you have that theoretical tool, and a lot of it is computational because of the complexity of the problem,
right.
but you solve a set of equations that from the physics that you know, or from the physics that you extrapolate to those those environments, and then you work it out. You say, okay, what should my light signature look like? And then you compare it with data. The other piece to this, like you mentioned, is accretion. So what happens to gas when you put it in the gravitational field of another star? This could be a black hole, this could be a neutron star, this could be a cluster of stars, whatever.
Right.
You ask, well, what happens to this gas? We know a little bit from just terrestrial experiments what happens to, the hydrodynamics, right? We have to know enough hydrodynamics to have our planes fly, we can study our oceans, etc. But of course, this is a completely new regime, but the same types of physics that goes into
Right.
the calculations there. So those are my secret tools, I would
Yes.
say, in my.
Oh, and
in my-
I can't resist the final question, because the math and the physics is well understood, and it's quite difficult. But most theorists I know have a part of their toolkit is physical intuition. How does that work, especially when you're dealing with the universe and you don't quite know what to expect? How
That's
do you
true.
tether yourself in knowing you're on the right track?
I think you have to first simplify your problem enough and just ask, what are the essential elements of this problem? What are the complications that I can get rid of? And then you...
The spherical cow.
The spherical cow,
Yeah.
exactly. Do I really need the fact that this is not a sphere, or do I really need the fact that it's hot? So you pare it down to its bones, and then you basically, different people do it differently. My PhD advisor has a way of pretending he's an electron.
Who's that?
Ramesh Narayan.
Oh, yes.
So, like, when you talk about physical intuition, he's
Yeah.
like, well, but if this beam is moving through this medium, and you're almost like
It's
are there.
visualization.
You're completely visualizing the problem, and you're saying, okay, how do I set this up so I do the right calculation?
Right.
So I think it develops over time with both solving a lot of different
Right.
problems and then comparing it with data and saying, okay, this is where I failed, this is where I succeeded. And yeah,
And that
it's
gives you the bravery to venture into an unanticipated or new situation and know that you're not untethered.
I think so, yeah. And it's amazing that I still find it developing, like speaking for myself, I could be considered mid-career, but I still feel like my physical intuition each year is better than it was the year before. Like I can look at the result of a calculation and say, no, this is not right, or or we haven't included enough complexity, or we've included too much. So it's just something that keeps on getting better.
Right. Okay, that's great. Thanks, Feryal.
Thank you.